Inverse trigonometric functions. Before we take a look at inverse trigonometric functions, let's do an algebra review and look at what is an inverse function in general. So if x comma y is a point on f, then yx is a point on its inverse. And here's the notation for f inverse. This is not read as f to the negative 1. So basically, if I have xy on f, then I switch their places, yx is on its inverse. And note that f must be 1-to-1 to have an inverse. So now, quick review, what does it mean to be a 1-to-1 function? Well, a function f is 1-to-1 if there is no horizontal line that can be drawn that intersects the graph of f in more than one point. So let's go and take a look at the graph here. It is one of our trigonometric functions. It is cosine. Notice it starts at the amplitude 1, so this is y equals cosine x. And we want to determine if this is a 1-to-1 function because we're interested in finding its inverse. So it says there can be no horizontal line that we draw that can intersect in more than one point. But if I draw just quickly a horizontal line here, I would intersect the graph definitely more than one time. So here, just looking at this portion of the graph, I'm intersecting 4 times, and of course it's periodic, so it keeps going, so it's going to intersect infinitely many times. So that means that the cosine graph is not 1-to-1, But we want to be able to find an inverse for cosine. So now we're going to talk about how do we define cosine inverse of x. Defining inverse sine, cosine, and tangent functions. To define inverse trig functions for sine, cosine, and tangent, what we need to do is to restrict their domain in order to obtain 1-to-1 functions. So let's continue to focus on the cosine graph. So here we have the cosine graph, just zoomed in on it a little bit. And what we're going to do is take just a portion. So a restricted domain means we're going to take just a portion of the domain. So we're going to take the portion from 0 to pi. So this portion here, we're going to go ahead and just keep that part of cosine. So that's indicated right here in the middle. So we're looking at y equals cosine x on the x values in the interval from 0 to pi. So that's what this notation means. So we're looking at just this select part of the cosine graph. And this part of the cosine graph is 1-to-1. If I draw a horizontal line anywhere, it's only going to intersect the graph one time. So this is, you can see, a 1-to-1 function, this piece anyways. So what that means is that I can find its inverse. So any point that I choose on this restricted cosine graph, I can switch the values of x and y to create cosine inverse. So just to focus on a few, this is the coordinate point 0, 1. This is the coordinate point pi over 2, 0. And this is the coordinate point pi, negative 1. So on the graph of cosine inverse, we should see those coordinate points where the x's and y are switched. So on the far right, this is the graph of cosine inverse of x. So if I go ahead and focus on a few key points, I can see this coordinate point up here, I go to the left 1, negative 1, and up pi. So this coordinate point is negative 1 pi. So we can see how from cosine x, I had an xy, and now it's yx on its inverse. Here I have the coordinate point 0, pi over 2, and then I have the point 1, 0. So we can see those values of x and y switching places. So here I have the graph of cosine inverse of x. Let's go ahead and focus on that inverse cosine graph and introduce an alternate notation. So arc cosine of x is equivalent to cosine inverse of x. So these are two notations that mean the same thing. Arc cosine x is equivalent to saying cosine inverse of x. And here's the same graph we looked at earlier. So again, we had that restricted domain that allowed us to find our cosine inverse graph. So let's just focus on cosine inverse right now. So if I take a look at this graph, let's remember how functions work. We have inputs, those are on the x-axis. So here, these are my inputs. So notice that my inputs are restricted from values -1 to 1. And the outputs, the values that can come out of my cosine inverse function, extend from 0 all the way to pi. So that is my range, and the inputs are my domain. So if I take a look down here in this bottom box, I have y equals arc cosine x, again equivalent to cosine inverse of x. Its domain, its possible inputs, are only from -1 to 1, including those values. And the range, the values that can come out, those y values, are only from 0 to pi, including 0 and including pi. So that means the values that come out of cosine inverse's outputs, can be found in quadrants 1 and 2 of the unit circle. So in quadrants 1 and 2, I extend from angles between 0 and pi. So I'm going to ask you to remember that cosine inverse outputs, the only values that can come out of cosine inverse, are in quadrants 1 and 2, specifically the angles 0 to pi. Let's take a look at an example. Find the exact value of each real number. Remember, there should only be one answer. So we have cosine inverse of 1/2. Now remember, inverses switch the inputs and the outputs. So what we're looking for when we're asked for cosine inverse of 1/2 is what value did I have to plug into cosine? So it's like cosine of what value, question mark, is equal to 1/2. So we solved actually equations that look like this before. So we solved, okay, what angle do I plug in to get out 1/2? But usually we solved this on the entire unit circle, on 0 to 2 pi. But because we're talking about cosine inverse, we have a restriction. The only outputs for cosine inverse are in quadrants 1 and 2, so angles between 0 and pi. So when we think about an answer here, we have this restriction. The answer can only be an angle from 0 to pi, and specifically an angle in radians, because it says find the exact value of each real number. So I do need my answer to be in radians. So the answer there is going to be pi over 3. So if I think about quadrants 1 and 2, cosine's only positive in quadrant 1, so my answer is going to be from quadrant 1, and that angle that I plug into cosine to get out 1/2 is pi over 3. So my other note here is, remember, there should only be one answer because cosine inverse is a function. So functions only output one answer. So we're not solving like we did in previous sections for two angles because that is on all of 0 to 2 pi, the whole unit circle. Cosine inverse is asking for a very specific answer that has to be from 0 to pi because of how we restricted our domain. In this next example, we want to find arc cosine of negative radical 3 over 2. So this is just an alternate notation for cosine inverse. We're still thinking the following. We're still thinking cosine of what value, question mark, is equal to negative radical 3 over 2. But again, I have to make sure, just point above, that this angle is between 0 and pi. So I'm limited to quadrants 1 and 2. These are the only quadrants where the outputs of cosine inverse, and that's what I'm trying to find, the output of cosine inverse, or arc cosine, what comes out right here, can only be from these two quadrants. Well, cosine would only be negative in quadrant 2 and the angle that I'm looking for here is going to be 5 pi over 6. So if we were to plug 5 pi over 6 into cosine, we would get out negative radical 3 over 2. And finally, arc cosine of negative radical 2 over 2. So again, we're thinking about cosine of what angle, question mark, is equal to negative rad 2 over 2. And that restriction on the angle is still 0 to pi. Anytime I have cosine inverse, arc cosine, they're the same thing, my answers can only come from these two quadrants. So, of course, that angle that we would substitute in to get out negative radical 2 over 2 is 3 pi over 4. So the answer to this last one is 3 pi over 4. Before we go any further, I have a huge warning. A common mistake that students make is thinking that sine inverse of x is 1 over sine x. So I want you to notice these are not equivalent for any of the inverse trig functions. And I think the confusion lies in the fact that in algebra, if I have x to the negative 1, that is 1 over x. That's because x is a variable that represents a number. So if I have a number to the negative 1, I can rewrite that as 1 over x. That is a property of real numbers. But this notation doesn't mean to the negative 1. It means inverse. So I can't apply this to a function. This isn't even the same type of idea. It's just a same notation, but in a different context. And so that's why hopefully it's less confusing if you use the arc notation. So arc sine of x, rarely when it's written like this do students write that as 1 over sine x. But when it's written as sine with this notation, inverse of x, students often put 1 over sine x, and that is not true, because if you think about it, 1 over sine x, we do know what that equals. That's cosecant x. And cosecant x is not the same as sine inverse of x. Let's move on and look at the inverse sine function, or arcsine of x. Now, just like arc cosine of x, or cosine inverse of x, we had to restrict the domain of the sine function in order to create a one-to-one piece that we could then switch the values of x and y to obtain our sine inverse function. So I'm not showing the development of this. I am, however, just showing the graph of sine inverse of x. So sine inverse of x looks like this piece here, because it's taking a piece of the original sine graph and switching the values of x and y. And notice that the input values for sine inverse extend from negative 1 to 1. That is the domain, negative 1 to 1. But the range values are different. The range values extend from negative pi over 2 to pi over 2. Negative pi over 2 to pi over 2. So they're different than cosine inverse. So if we think about the outputs, the range for sine inverse, negative pi over 2 to pi over 2, those values come from quadrants 4 and 1. So we can see down here, negative pi over 2, negative pi over 3, negative pi over 4, negative pi over 6. Those are our common reference angles. And then we have our quadrant 1 common reference angles, pi over 6, pi over 4, pi over 3, and pi over 2. So our sine inverse outputs can only be from these values here. So negative pi over 2 all the way to pi over 2. And what I want you to note is that you cannot use any coterminal angle to these angles down here. So what do I mean by that? So while it is true that negative pi over 6 is coterminal to 11 pi over 6, we are not, I repeat, we are not allowed to say that 11 pi over 6 is an output to sine inverse. We are very strictly bound to these range values being from negative pi over 2 to pi over 2. Let's do some examples with sine inverse. So we're going to find the exact value of sine inverse of 1/2. So again, what we're thinking about to find this exact value, we're thinking sine of what is equal to 1/2, because we're switching the values. Normally, we would find the output of sine, but since we're doing inverse, we're thinking about the input. What are we plugging into sine to get out 1/2? But we're restricted. So this value can only be between negative pi over 2 and pi over 2. Well, sine is positive in quadrant 1 out of these two possible quadrants. I have to find my angle from quadrant 1. So that angle that I plug into sine to get out 1/2 is pi over 6. So sine inverse of 1/2 is pi over 6. For arcsine of negative radical 2 over 2, again I'm thinking about sine of what angle, question mark, is equal to negative radical 2 over 2. My answer from quadrant 1 or 4 as a possibility has to be from quadrant 4. That's the only place where sine is negative. And if I want an output of radical 2 over 2, well, that reference angle is pi over 4. So the answer has to be negative pi over 4. So over here, negative pi over 4. And it is not an option. It is not the same to write 7 pi over 4. Even though those are coterminal angles, arcsine or sine inverse had a very particular restriction for its output. So it has to be the negative versions of the angles. And finally, on the last part, we are asked to find sine inverse of negative 1. So again, it's that we're thinking about sine of what value outputs negative 1. So that's going to have to be, again, down here. So it's not actually in quadrant 4, it's the quadrantal angle negative pi over 2, because remember this coordinate point is 0, negative 1. So the y value, sine, is negative 1 down here at the angle negative pi over 2. And as a reminder, I cannot put 3 pi over 2. So I cannot use the positive angle, the coterminal angle. I have to use negative pi over 2. Now, I could use negative 90 degrees if the problem didn't say we need real number answers. So just like that last example, this part here means that I do want my answer to be in radians. And again, there should only be one answer because these are functions. So we have an input and just one output. Now let's look at the inverse tangent graph. So y equals arctan of x, or tan inverse of x. So how is this graph obtained here? Well, if I take a look at the regular tangent graph, or recall tangent, at least one period of it, we have to restrict it as well between negative pi over 2 and pi over 2. It's vertical asymptotes. So if we switch those coordinate points, those x, y's on this tangent graph, we obtain the graph of tangent inverse here, where notice I now have a horizontal asymptote at negative pi over 2 and another one up here at pi over 2. And this graph here, I'm going to go ahead and include the special note that you do have to memorize this graph. This is a graph that absolutely appears in future classes more so than the graphs of arcsine and arccosine. So this is absolutely a graph that you need to have committed to memory. So now let's look at its properties. Its domain, so if I look at this, it does continue on to the right and left forever. So its domain is all real numbers, negative infinity to infinity. But its range, its outputs, extend from negative pi over 2 to pi over 2. But not including those values. So we have open parentheses around negative pi over 2 to pi over 2. So very similar to the sine inverse outputs, the tan inverse outputs are in quadrants 1 and 4. Again, they have to be those negative angle values down in quadrant 4, but they exclude pi over 2 and negative pi over 2. Those are not possibilities for tangent inverse. In this example, let's go ahead and again find the exact value of each real number, this time focusing on tan inverse or arctangent. So arctangent of 1. We are thinking about tangent of what angle is equal to 1. But again, we're limited. Our value can only come from negative pi over 2 to pi over 2, or quadrants 1 and 4. Well, tangent would be positive in quadrant 1, and the angle that we would substitute in to get out 1 is pi over 4 in the tangent function. So arctangent 1 is pi over 4. If we're looking at tan inverse of 0, we're thinking about tangent, again, of what angle in radians is equal to 0. Well, that value is just 0, and that is included from negative pi over 2 to pi over 2. 0 is included, so tangent of 0 in radians is equal to 0. So that is my answer. And lastly, tan inverse of negative radical 3. So tan inverse of negative radical 3 is asking me to think about tangent of what angle is equal to negative rad 3, but restricted from that negative pi over 2 to pi over 2. Well, that's going to leave me to choose my answer from quadrant 4 because tangent is negative in quadrant 4, and that angle that we would substitute in to get out negative radical 3 would have to be negative pi over 3. So tan inverse of negative radical 3 is negative pi over 3. Now, just to sort of summarize and recap here, this work on the right-hand side has been sort of scratch work. And these values, arctangent of 1 equals pi over 4, is really a matter of understanding our evaluating trig functions in reverse. So in other words, it sort of partners with the thought that tangent of pi over 4 equals 1. So we're switching their places. Notice we would typically be asked tangent of pi over 4, and we'd have to give the value of 1. So now on the inverse, arctangent of 1 means work the opposite direction. What angle did I have to plug in? So it's that idea of switching it back and forth that really proves that we know the unit circle sort of in this forward and backwards direction. And the one piece that it includes on top of that is that there's certain restrictions. So cosine inverse can only be from quadrants 1 and 2. Sine and tan inverse can only be from quadrants 1 and 4. And the angles in quadrant 4 have to be the negative versions of the angles. So now we do have inverse functions for the remaining trig functions. We have cotangent inverse, secant inverse, and cosecant inverse. We won't focus on their graphs at all. We are just going to use this chart here to determine the range values. So the values that can come out of these inverse trig functions here. So in this example, we're going to find the degree measure. So this time we're going to use degrees instead of radians. Find the degree measure of theta if it exists. So this is just another way of asking the same types of questions from earlier. So theta is equal to arc cotangent 1. So it's essentially like asking for arc cotangent of 1, I'm just giving it a name, calling it theta. But what I want to do here is focus on a way to rewrite this statement. So if theta is equal to arc cotangent 1, then what we know, because inputs and outputs switch places on cotangent, we know that cotangent of theta equals 1. But on the interval, so theta is restricted to values. Let's look at cotangent inverse, because after all, that's what we're truly finding the value for. Cotangent inverse is restricted from 0 to pi. So theta can only be from 0 to pi. So this statement here is equivalent to this one here. So now we can think about solving this type of statement like we did in previous sections. So where does cotangent theta equal 1? Where theta is from 0 to pi, so in quadrants 1 and 2. Well, instead of dealing with cotangent, let's rewrite this as 1 over tangent theta is equal to 1. Well, that's just tangent theta is equal to 1. So what do I have to plug into tangent to get out 1 between 0 and pi? Or in quadrants 1 and 2? Well, it has to be quadrant 1, and it has to be an angle of pi over 4. But we are thinking in degree measures, so that's 45 degrees. So theta is 45 degrees. So here, very similar to what we were doing earlier, what's slightly different is we're just saying arc cotangent of 1 equals some angle, call it theta. And then at the end, we're saying theta equals 45 degrees because this time we're being asked for degree measure instead of real number. Try it one more time. On the right-hand side here, I have theta is equal to secant inverse of 2. So an equivalent statement to this would be to say, well, if inputs and outputs switch on the secant graph, secant theta would have to be equal to 2, but restricted to where I'm on the interval, theta is on the interval from whatever the range of secant inverse is. So that's going to be from this 0 to pi over 2, not including pi over 2, and pi over 2 to pi. Well, once again, now I am going to avoid using secant and switch myself over to cosine using a reciprocal identity. 1 over cosine equals 2 over 1. Cross multiplying, or taking the reciprocal of each side, let's solve instead cosine theta equals 1/2. So here, if I think about in quadrant 1 or 2, 0 to pi over 2 is quadrant 1, pi over 2 to pi is quadrant 2, so we're forced to look at quadrant 1. What angle do I plug in cosine to get out 1/2? Well, that's pi over 3. Again, we want degree measure, so pi over 3 in degrees would mean theta is equal to 60 degrees. So we're going to be using that technique of rewriting this type of equation here into this sort of equivalent equation here, the second step. So we're going to be seeing that in just a bit. Let's move on to some different types of examples. We're going to evaluate without using a calculator. We're going to express our answer as a real number. So here we have sine of tan inverse of 3 over 2. We have a composition, and I have to work inside first. I have to first focus on evaluating tan inverse of 3 over 2. So what I want you to automatically recognize here is that when we're evaluating an inverse trig function, our answer is some angle. So what I'm going to do is I'm going to go ahead and think about this as some angle theta. So we're thinking, remember what we're thinking, tangent of this angle theta is equal to 3 over 2. So I'm going to go ahead and pull that off to the side. So I'm going to say tangent of theta is equal to 3 over 2. That's what we're thinking about. But there's no angle that we have in our typical reference angle values that we substitute into tangent to get out 3 over 2. Doesn't mean there's no answer because this is a possible statement. Tangent can equal 3 over 2. The range of tangent is all real numbers. It's just we don't know it without a calculator and we're not supposed to use one. So tangent of theta equals 3 over 2. That's where I'm at, and I can't evaluate it directly. But now what I want you to do is think about what this statement looks like now. So this is now sine of theta. This is now sine of theta. So I replaced this whole quantity with theta. We don't know what theta is yet. But what we can do is we can draw a triangle in the appropriate quadrant using this piece of information that I know about theta. So tangent inverse can only come from quadrants 1 and 4, and since tangent is a positive value, tangent of theta is positive 3 over 2, I'm going to go ahead and draw my reference triangle here in quadrant 1. So here's going to be my reference triangle. Here's going to be my theta. What I know about theta is tangent, so that's opposite over adjacent, is what I can set up in regards to this angle theta. So opposite is 3 and adjacent is 2. So this original problem here was asking us to find sine of some angle. Well, we couldn't find that angle exactly, but we could draw a triangle regarding that angle, and now let's find sine of theta. Remember, sine is opposite over hypotenuse. So if I can find this hypotenuse right now, I can find sine of theta without ever having found theta exactly itself. So to find this side length, let's go ahead and call it z, we use the Pythagorean theorem. So 2 squared plus 3 squared equals z squared, or 13 equals z squared. So we get plus or minus radical 13 is z. We take the hypotenuse to be the positive one, so we get the square root of 13. So sine of theta, it turns out, is opposite 3 over the square root of 13. Rationalized, we get 3 radical 13 over 13, multiplying that top and bottom by radical 13 to rationalize. So this is definitely a different type of problem, and the big piece that I want you to take away is the idea that when we're evaluating a trig inverse function, we need to understand that our answer is an angle. Sometimes it's an angle that we're familiar with, like pi over 3, pi over 4, pi over 6, but sometimes it's some angle that we don't know offhand without using a calculator. But there's at least enough information to construct a triangle to find all 3 side lengths and evaluate some other trig function regarding that angle. In this example, let's evaluate cosecant of tan inverse of -1. So once again, we look at the inside and attempt to evaluate tan inverse of -1. Since this is an inverse trig function, we know that our answer is some angle. Let's call it theta. So what we know then is that tangent of theta is equal to -1. So we're thinking tangent of what angle equals -1, but restricted to the interval where theta is between -pi/2 to pi/2. Because we're talking about tangent inverse, there was a restriction. Since tangent is negative, our answer has to be in quadrant 4. So the angle that we plug into tangent to get out -1 in quadrant 4 has to be theta equals -pi/4. Remember, we cannot put 7 pi/4, so we have to say the negative value, -pi/4. So this was the best case scenario. In other words, we didn't have to draw a triangle, so we can find this value exactly. The previous one, when we had tangent theta equals 3/2, we didn't have an answer for that offhand. We would have needed to use a calculator. But here we know the value is -pi/4. So this problem becomes, we're going to replace this whole inside. Tan inverse of -1 was theta. Well, look, we just found theta was -pi/4. So this problem becomes cosecant of -pi/4. And now we're just evaluating a regular trig function like we did for the past couple chapters. So cosecant of -pi/4, let's go ahead and rewrite that using a reciprocal identity, 1 over sine of -pi/4. And let's go ahead and pull out the negative because sine is an odd function. So I have 1 over negative sine of pi/4. And then sine of pi/4 is radical 2 over 2. So we have 1 over negative. Now it is radical 2 over 2, or it's 1 over radical 2. Why am I choosing that version, 1 over radical 2? Because I'm going to have to flip it, multiply by the reciprocal right now. So the answer is just negative radical 2. The answer is just negative radical 2. So we did not need to draw a triangle because we could evaluate this tan inverse of -1 exactly. We know theta is -pi/4.